Intrinsic semiconductors. Semiconductors, as we know, are the materials with conductivities lying between conductors and insulators. Silicon or germanium, most commonly used as semiconductors, occur naturally and are the pure semiconductors. These pure semiconductors are known as intrinsic semiconductors. The atoms of intrinsic semiconductors are closely grouped together in a crystalline pattern called a crystal lattice. Let us consider the crystal lattice of silicon. This is a diamond-like structure. Each atom is surrounded by 4 nearest neighboring atoms. We know that each silicon atom has 4 valence electrons. In its crystalline structure, every silicon atom shares one of its 4 valence electrons with each of its 4 nearest neighboring atoms and also takes share of 1 electron from each of its neighbors. These shared electron pairs form covalent bonds. The figure schematically shows the 2-dimensional representation of a silicon structure at low temperatures. It shows an idealized picture in which all the covalent bonds are intact. As the temperature increases, more thermal energy becomes available to the valence electrons. As a result, some of the electrons may break away from the covalent bonds, thereby becoming free electrons. These free electrons contribute to conduction. Such breaking away of an electron from a covalent bond creates a vacancy in the bond as shown. If the free electron carries charge minus Q, it leaves a vacancy with an effective charge plus Q. This vacancy with the effective positive electronic charge is called a hole. An electron from the nearest covalent bond escapes and fills the hole, thereby creating a hole at a new position. The process continues, and this way the hole behaves as an apparent free particle. Thus, in intrinsic semiconductors, there are 2 types of free charge carriers: electrons with a negative charge and holes with a positive charge. The number of free electrons in E is equal to the number of holes in H. The concentration of electrons or holes is also known as intrinsic carrier concentration. When an external electric field is applied to the intrinsic semiconductor, the electrons start moving towards the positive terminal of the battery and the holes start moving in the opposite direction, that is towards the negative terminal of the battery. The movement of electrons gives rise to an electron current, IE, and the movement of holes gives rise to a hole current, IH. The total current I in the semiconductor is the sum of the electron current, IE, and the hole current, IH. Let us now understand the conductivity of an intrinsic semiconductor at 2 different temperatures with the help of an energy band diagram. This is how the energy band diagram of an intrinsic semiconductor looks like at temperature of 0 Kelvin. All the electrons are in the valence band and the conduction band is empty. An intrinsic semiconductor will behave like an insulator at T equal to 0 Kelvin. The energy band diagram of semiconductors for T greater than 0 Kelvin is as shown in figure B. It is the thermal energy which excites some electrons from the valence band to the conduction band at higher temperatures. These thermally excited electrons at T greater than 0 Kelvin partially occupy the conduction band, leaving equal number of holes in the valence band. The free movement of the electrons in the conduction band contributes to the electrical conductivity of the intrinsic semiconductor, and it starts behaving as a conductor. Let's recap. The pure semiconductors, silicon or germanium, are known as intrinsic semiconductors. The atoms of intrinsic semiconductors are closely grouped together in a crystalline pattern called a crystal lattice. In intrinsic semiconductors, there are 2 types of free charge carriers: electrons with a negative charge and holes, vacancy, with a positive charge. In an intrinsic semiconductor, the concentration of free electrons and holes is equal. Under the action of an external electric field, the total current in the intrinsic semiconductor is the sum of the electron current and the hole current. An intrinsic semiconductor behaves like an insulator at temperature of 0 Kelvin and like a conductor for temperatures greater than 0 Kelvin.
Extrinsic semiconductors. In intrinsic or pure semiconductors, the carrier concentration of both electrons and holes at normal temperatures are very low. Hence, to get appreciable current density through the semiconductor, a large electric field should be applied. This problem can overcome by adding suitable impurities into the intrinsic semiconductors. The extrinsic semiconductors are those in which impurities of large quantity are present. In general, the impurities can be either 3rd group elements or 5th group elements. Based on the impurities present in the extrinsic semiconductors, they are classified into 2 categories: 1. N-type semiconductors and 2. P-type semiconductors. N-type semiconductors. In order for silicon crystal to conduct electricity, we need to introduce an impurity atom such as arsenic, antimony, or phosphorus into the crystalline structure. These atoms have 5 outer electrons in their outermost covalent bond to share with other atoms and are commonly called pentavalent impurities. This allows 4 of the 5 electrons to bond with its neighboring silicon atoms, leaving one free electron to move about when electrical voltage is applied. As each impurity atom donates 1 electron, pentavalent atoms are generally known as donors. Antimony, Sb, is frequently used as pentavalent additive as it has 51 electrons arranged in 5 shells around the nucleus. The resulting semiconductor material has an excess of current-carrying electrons, each with a negative charge, and is therefore referred to as N-type material, with the electrons called majority carriers and the resultant holes minority carriers. The block diagram of N-type impurity doping and corresponding band diagram is shown in Figure 1. P-type semiconductors. In contrast to N-type of semiconductor, if we introduce trivalent 3-electron impurity into the crystal structure, such as aluminium, boron, or indium, only 3 valence electrons are available in the outermost covalent bond, meaning that the 4th bond cannot be formed. Therefore, a complete connection is not possible, giving the semiconductor material an abundance of positively charged carriers known as holes in the structure of the crystal. As there is a hole, an adjoining free electron is attached to it and will move into the hole to fill it. However, the electron filling the hole leaves another hole behind and is forth, giving the appearance that the holes are moving as a positive charge through the crystal structure, conventional current flow. As each impurity atom generates a hole, trivalent impurities are generally known as acceptors, as they are continually accepting extra electrons. Boron, B, is frequently used as trivalent additive as it has only 5 electrons arranged in 2 shells around the nucleus. Addition of boron causes conduction, which consists of many of positive charge carriers, results in a p-type material, and the positive holes are called majority carriers, while the free electrons are called minority carriers.